Multiple regression analysis global test of the model. The global test is used to investigate if any, of the independent variables have significant coefficients. If you recall from chapter 13, we not only ran regressions for the first time, we then tested the beta. I mean, if you recall that, I'm sure. And in the test of the beta, right, we had to find out a few things. We had to find out, what the t-stat was, the critical t, then we had to, calculate the computed t and compare those. And then we found out if our computed, for example, was higher than our critical, hey, right, we reject the null hypothesis. And the null hypothesis was that beta was equal to 0. And if we reject that, then beta is not equal to 0 or greater than 0. Then whatever our beta was in the previous chapter's case, it was 0.26. Turns out that was what we call statistically significant. Okay, so that's the same kind of framework we're using here, except we call it the global test. Okay, so the global test right there. If any of the regression coefficients are not equal to 0. So after we get all of our betas, what do I mean, get all of our betas? I mean that when we have our regression output and that output gives us a certain amount of betas, and I should limit that to this. When that regression output gives us those betas, the question is, are they stat sig? Are they statistically significant? And that's what the global test is trying to help us understand. So state the null hypothesis. And that null hypothesis is that the null hypothesis is that all the betas are equal to 0. And what does that mean? What does that mean generally, that the betas are equal to 0? Is there anything other than beta being 0 that it represents?
It would mean that there's no correlation, right?
Between what?
Between X and Y?
Exactly. Keeping in mind that, the beta is just telling us about some correlation, right, between X and Y. So if we are saying that beta equals 0, then we're saying that X cannot explain Y, right? There's no relationship between the two. However, right, we have seen in the final results here that indeed all of these have some number, right? They all have some number, right? 4.583 is not 0. 14.83 is not 0. 6.101 is not 0. So the fact that they all explain, or they're all not 0, suggests that our alternate hypothesis may be the one we hope comes out as statistically true or statistically significant. Okay, so that's just an idea of where we're going here. Let me go right here. Where are we? So when I say HO represents the fact that beta 1, 2, how many number of betas you have are all 0, as you just said, Mr. Trejo, that surely there is no correlation. But we found one when we ran the regression. So our analysis has turned out that H1 seems to be closer to true based on the initial regression that we ran. Okay? Not all betas are equal to 0. So let's find out. Okay, or at least let's go down this road. Number 2, decide on your alpha. Your alpha is 0.05, your most popular alpha. Step 3, select the appropriate test stat. Okay, so we're going to use the F test because we're looking at the global test. You have to remember, right, that the global test, right, leads us down the road of F's, not T's or Z's, but F. Formulate a decision rule. And the F test is a K, which we know is number of treatments, and N minus K plus 1, which we remember as your sample size minus your treatments plus 1, degrees of freedom. Okay? similar to what we looked at in earlier chapters. We know that in order to formulate a decision rule, we have to then compare our critical T or our critical F, okay, which is right here, critical F with our computed F, which is right there. So we have to compare those two numbers as per usual. Step 5, take a sample, do the analysis, arrive at a decision. So if we go back to our summary output, we can see some of the things that will be helping us. And let's look right here. Based on the F statistic of 21.90, okay, 21.90, reject the null hypothesis. So the first thing we have to ask ourselves is, why in the world are we rejecting? Because we have to first understand what is our critical F. And in this case, we see the establishment of our rejection region right there of 3.24. We do know that an F distribution, the family of F's, is a right-sided positive distribution. Okay, it still has normality associated with it, but we do not go to the left side. Okay, so all of our alpha, okay, will be on that right side, meaning we're not necessarily going to be taking it by 2 or divided by 2. Okay, so if you implement your standard formula of f.inv.rt and we use 3 and 16, we then can find our 3.24. Now remember, right, let's go to this 3 and 16 real quick. It says that you must be using a k and n minus k plus 1, right? That's going to be your numerator and your denominator, okay, in terms of your degrees of freedom. Now, you can either think about it, and you should. Let me start it off like this. You should say to yourself, okay, what is k? K is number of treatments, right, which is your number of variables that are in play. In other words, your independent variables. Well, how many independent variables do we have? Well, we have 3 independent variables. How do I know that? Because they are right here. 1, 2, 3. Temperature, insulation, and age. Those are our 3 independent variables. Okay? Now, if I know that my k is 3, then I use that as my numerator. So k is 3 right there. Once I get sophisticated enough, once I've practiced this enough, once I've practiced this enough to the point where I can eyeball the ANOVA table, things are going to speed up for me. Okay, what do I mean? Well, here it is. Here's your 3. That's the same 3 that I just found by counting my independent variables. Okay? So as you practice this, just keep in mind your ANOVA table gives you a wealth of information to construct your hypothesis test. So degrees of freedom 3 is right in front of me. Okay, so when I'm looking for my F, where I'm implementing f.inv.rt, I know, right, I need a 3, I need an alpha, I need a 3, I need a 16. So this is my denominator, n minus k plus 1. I can eyeball it, okay, and I can say, I can see what my n is, right? I can see what my k is. What's n in this case? How many n do we have?
Isn't that the number of observation that we have with 20?
Okay, so let's hold on to that 20. What is my k?
Your temperature, insulation, and age is would be your 3 different treatments.
Okay. And if that's 3, then this, of course, must be 20 minus 4. And if it's 20 minus 4, that's 16. Okay, if it's 20 minus 4, that's where we're getting the 16. Okay. So that 16 is my denominator. But guess what, folks? You don't have to think about that too much once you get to the point where you've practiced this, and you can see there's my 16. So as you're implementing your F dot I and v dot RT, right? And you're thinking about, okay, what's my numerator? What's my denominator? They are right in front of you, right off of that table, right off of the table, 3 and 16. Okay, when you first start this, you may just begin to, okay, I have to think about what's my K, what's my N, let me do some quick math, okay, I got it. And it might take you, a minute or two, but the more you practice, once you begin to eyeball, okay, there it is, 3 and 16, move forward to the next thing. Okay, so that's where that practice comes in, and you should begin to start thinking about it in that way so that you can speed up the process of each question. The goal is not to be fast. The goal is to be accurate, of course, but it's a test. So all tests have time limits. So you want to exploit all of the productivity opportunities that exist from the ANOVA table. Okay, so if I exploit those productivity opportunities, there's a huge exploitation right there. Okay. All right. Now, once again, we do that in Excel. Or you could use your chart because there is a point, I think there's a 0.05 in the chart, but I tend to focus on Excel when it comes to these critical values. We've established the critical value of 3.24 right there. And now the question becomes, does my computed F fall in that region of rejection? So I need a formula for that. Okay, Excel does not have a built-in formula for the global test of the computed F. Okay, and I can even put that here, computed F. That's my computed F. So I need a formula, and there it is. SSR, okay, sum of squares regression, divided by your number of treatments, your number of independent variables, 3, all divided by SSE, right? Sum of squares residual. Keeping in mind, as I said in the last week, and it's on the video if you've been watching them, that Excel tends to output this language and even other language, but we know that SSE, right? Error, residual, kind of the same thing. That's what we have to understand this as. Okay, so SSE divided by what? Well, 16. What's 16? My denominator. What's my denominator? 20 minus the summation of K plus 1. Okay, so 20 minus the summation of 3 plus 1. And of course, now you're saying to yourself, well, wait a minute, right? Isn't that right here and right here? Absolutely. So take those two numbers, and you can see how this is logically playing out, right? There's a beautiful logic here that is playing out. So if we take those two numbers over each other, right, we're going to get a 21.90 as our computed F. Now, 21.90 falls to the right, okay, falls to the right of our critical F of 3.24. And so because it does fall to the right, and because 21.90 is greater than 3.24, we are in the region of rejection. We are in the region of rejection. What in the world are we rejecting? We are rejecting the null hypothesis. Reject the null hypothesis. What is our null hypothesis? Take a step back. Here's our null hypothesis. So we are rejecting the fact that the beta 1, 2, and 3 are all equal to 0. Okay, that they're all equal to 0. Okay. Now look at how I said that they're all equal to 0. What then could be the case? If I'm saying I'm going to reject the fact that they're all equal to 0, what is still possible?
That only some are equal to 0?
Yeah.
Not all?
Right. If HO is saying that they're all equal to 0, it's still possible that somebody is not zero, right? Look at the alternate hypothesis. Not all betas are equal to zero. Okay, so we've gone down a road, but not all the way down. Okay, just because of the way that the hypothesis test is set up. All right, so we reject the null hypothesis that all of them are equal to zero, and then we interpret some results here. So the interpretation is the results of the global test of the multiple regression analysis equation show that at least one of them is related to heating cost. Okay, at least one of the independent variables is related to heating cost. So we are saying, okay, we know that at least one of them is not zero. Okay, one of them is not zero. Are all of them not zero? Well, we don't know that. But we know, based on the fact that we've rejected the null hypothesis, that at least one of them is not zero. And if the beta, okay, if one of these beta, let's call BK, if one of them is greater than zero, okay, or I could also say is not zero, then we would call that statistically significant. Okay, in other words, one or more of the variables explain the variation in the dependent variable heating cost. We know that at a minimum, one of them does. Beta 1, is it beta 2, is it beta 3? We know that's a definite. The other thing is, it's possible that all three of them are not zero. We don't know that yet, but we do know that at least one of them is not zero. So there's a very important distinction there between saying not all of them are equal to zero and which one exactly is equal to zero. The global test is the first, you may have gotten that impression, right? We're just kind of getting started, of the multiple regression equation. If we fail to reject the null hypothesis, we would stop our analysis of the relationship between the dependent and independent variables with this sample and variables. So what we're saying is, if the HO, okay, that's all the betas, let me just put BK, are equal to zero, all the betas are equal to zero. If we can't reject that, if we find out that that's a good piece of information, effectively we're done, right? If we fail to reject the null hypothesis, meaning we do not reject HO, we would stop our analysis, right, with this sample and variables, because all we can say is, right, they're equal to zero. We can't go any further. It is possible that we would attempt a new study designed to predict home heating costs with different independent variables and a new sample of homes. That's because our first study would have showed us that these betas aren't any good. Our first study would have showed us that these betas are all equal to zero, right? And that doesn't help us, because if they're equal to zero, then there's no predictive power of the multiple regression analysis equation, okay? Because the betas are equal to zero. So if the betas are equal to zero and the betas are telling me something about, right, this relationship, but they're equal to zero, then a change in X has no influence on the change in Y, okay, because it's zero. So I could say, right, as X increases by 1, right, that's a big old zero. That's a big old zero. And if that's the case, then the X-Y relationship doesn't add much value to what I'm trying to do, what I'm trying to predict. So what do you do if that's the case? Well, we got to find some more data, okay? You got to find a new study to accomplish your goals. Maybe your first set of data just was bad data, right? You just happen to pull some bad data. But get some more data, right? Get some more observations going. The less observations you have, the more problems you're going to have with data analysis, because if you happen to get very little data and that data is biased or bad, then your outcomes are going to be biased and bad. But if you can get, instead of 20 observations, 40, 60, 80, 100, then it's highly unlikely that all of that data is going to be bad. Okay, and the chances of getting good data increase the more data you get. That's why we always say with sampling, get as much in as you can. It approaches normality, and you can accomplish more in your data analysis. Okay. Instead, our finding of a significant relationship leads us to the next logical question: which independent variables are significantly related to heating costs? Okay, so now we're just saying let's test the different betas. We've established the fact that they are not zero, okay, or at least one of them is not zero. Let's test them all. Number one, state the hypothesis. Okay, state the hypothesis. And going back to our original statements from before, last week, there you go. Decide on a level of significance, alpha. We're going to use the test T as usual, okay, with n minus k plus 1 degrees of freedom. We're not fearful of that because all we got to do is look at our ANOVA table and we're done. Formulate a decision, okay? And if we're looking at the decision from this perspective, again, we're going back to the fact that this will be greater than, less than or equal to, right? And this will be greater than, okay? Reject HO if T is, your computed T is greater than a critical T of 2.12. So at this point, I'm hoping you know how to easily get the 2.12. If you're looking at a two-sided test, you're dividing it in half. If you're looking at a one-sided test, you're using alpha as is, okay? And that's always been the case. So we get 2.12 as our critical T, and then all we need to do is find our what? Computed T. Do we have a formula for that? Well, we learned the formula last week. Bam! There's your formula. And if you don't like formulas, then go ahead and eyeball the summary output. Okay, and if you eyeball that summary output, okay, here is negative 5.934. And where do I find that in my summary output? Oh, look at that. Negative 5.934. Here is negative 3.119. There it is right there. And then, of course, 1.521 is right there. Now, sophisticated folks are able to interpret. So, our benchmark, okay, or our rejection region started at this number, 2.12. Okay, so 2.12 positive and negative represents our rejection region, okay? So negative 5.934 is less than 2.12. So negative 5.934 would fall in our rejection region. Graphically, negative 2.12 and 2.12, okay? Establishing our rejection region. And we see that negative 5.934, right, is right here. So what do? Reject the fact that beta 1 is equal to 0, and do not reject the fact that beta 1 is an actual number, right? What is the actual number of beta 1? 4.583. And so we say, okay, this is a good number. This number is statistically significant. Okay, that number is statistically significant because we've proven that it is not 0. It actually is greater than 0. So we take negative 4.583 as our actual number for the beta. Okay, great. Now, what about the other numbers? Well, negative 3.119. Negative 3.119. That too. Okay, let me get rid of this. 3.119 is actually falls in the rejection region on our left side. So we reject, okay, we reject the fact that beta 2 is equal to 0. So what is beta 2? Well, the number that we've gotten from the output. Beta 2 is 14.83. Okay, so 2 rejections, there we go. The third one, 1.5, beta 3 is the t-stat for beta 3, 1.521. Okay, now that would fall to the left of the number, to the left of the critical t. If that's the case, we cannot reject beta 3 being 0. And so we say then that beta, let me move this out the way. We say then that beta 3, age being having a beta of 6.101 right here, is statistically insignificant, meaning that's not a good number, because we have proven that 6.101 is actually 0. We've proven that beta 3 is closer to 0 than it is 6.101. So we can't use 6.101 in our analysis. We can use the negative 4.583. We can use the negative 14.83, but we're going to throw the 6.101 away because we couldn't prove that it's not actually 0. Couldn't prove it. So bottom line is that even though you may say and you may claim through hypothesis testing, if you set up a claim that beta 1, beta 2, etc. are equal to 0, and you end up rejecting that claim, and you do not reject the fact that not all betas are equal to 0, you're not done. Or how do we test how many betas are not 0? That's where we go to this process here, testing of the betas. So big 2 things happening. The first thing is running a global test, right? The first thing is running a global test. And the running of the global test is just allowing us to ask that question. Are the betas 0 or are they not 0? Okay. After we run the global test, we then go deeper and ask ourselves, well, which betas are 0 and which betas are not 0? Okay, that's the point of that story. Interpret the results. The test for each of the individual regression coefficients show that 2 independent variables, right, these 2 right here, mean outside temp, inches of insulation, are stat sig, are significant. One of them is not, okay, and that was age. In fact, the results suggest that we can eliminate age of furnace from the analysis. We then redo the multiple regression analysis without the age of furnace, okay, because it's not stat sig. And if that's the case, we rerun the regression with just temperature and insulation, okay? And after we run it, the numbers change a bit, and we should get a better idea of what impacts heating cost now that we've removed a factor that was not significant. The regression equation is now only including mean outside temp and inches of insulation. And we see the numbers did change a bit, and that's what we would go with as our explanatory power. Then, of course, as you learn more about this, you would ask yourself, like I said earlier, what in the world, what else explains heating costs? And you would throw maybe those in for the next analysis and then run global test and then test the betas going forward.